Hi, welcome back. In this video, we will conclude with learning about the 3 different rocks, with finishing up with metamorphic rocks. So, just as a review, minerals form in 4 different ways. There's precipitation reactions. Those form only sedimentary rocks. Crystallization from magma forms lava or magma, forms only igneous rocks. Metamorphic rocks form from the final 2, hydrothermal solution and heat and pressure. But as we'll see, heat and pressure can actually kind of be separated into 2 different things. Really, if you have one, you have the other, but there sort of is a slight difference between the kind of metamorphism that heat can have and the kind of metamorphism that pressure can have. I'll show you. So the definition of metamorphism in general just means to change form. So we know of animals like a caterpillar metamorphosizes into a butterfly, a tadpole metamorphosizes into a frog or a toad. With rocks, the way a rock metamorphosizes is its chemical composition is either altered in a way or the minerals reform. An example I give with this with my students in biology class is, say we had a Lego house, a bunch of Lego bricks put together as a house, and we take every piece apart. Do we have to form a house again, or can we use those bricks to build something else? We can absolutely use those bricks to build something else. So with metamorphism and minerals are made of elements. Now the raw ingredients, the elements are there, and they combine together in specific ratios to form specific compounds, minerals. But with the addition of lots of heat and pressure, the atoms and minerals can create new forms. They may be allotropes of the same thing, or of the same kind of substance, or they may just recrystallize into completely different chemical formulas. That's possible. Now with hydrothermal solution, we are actually adding new things to the rock. We'll get to that in a bit. For the most part, metamorphism happens deep below the ground, and metamorphic rocks do not make up much of the surface of our planet. I think it's about 12% of the surface of the Earth. Now, we'll start with, I believe we'll start with heat here in formation of metamorphic rocks. The heat that forms a lot of these metamorphic rocks would normally melt the minerals, but the pressure is so intense deep below the lithosphere that the pressure does not allow the material to flow like magma actually does. And I alluded to this earlier, but the existing minerals within the rock can rearrange and form brand new ones. So one kind of metamorphism, and this is the emphasis on heat, is contact metamorphism. So you may have a magma chamber underground, a body of molten rock. Rocks around it are going to be heated extremely by that. But if they're far enough away from the magma source, or if the pressure is high enough, then those minerals that are the rock and mineral that surrounds the magma chamber don't necessarily melt themselves, but they are baked in a way, you can think of it, and they are completely changed. When you put cake batter into the oven, what comes out is really very different from cake batter, structurally and chemically and all of that. All the pieces are still there, they've just been rearranged into a new form. So around this magma chamber, we can see that there's different degrees of metamorphism. Limestone is the original unaltered sedimentary rock. Now, if limestone has what we call maybe low-grade metamorphism, high temperatures, high pressure, but not crazy high, that may produce marble, which has calcite minerals within it. If you increase the temperature and the pressure, then you can perhaps get calcite, chlorite, and serpentine out of this. I have some serpentine right here. So the minerals have been, oops, that's gonna get covered up. We can see the minerals are pretty distinct. So I think this originally starts off as sort of a uniform looking rock, but then the heat and pressure forces the minerals to separate from each other. And then it forms these really cool little structures. And with very intense metamorphism, we may get garnets, which are fairly precious gemstones, and diopside, which is just another kind of rock and mineral. Here's a picture of a place where you can see the contact metamorphism. That would be an igneous body throughout there, so some sort of cooled igneous rock. But on either side of it, we can see how whatever this other rock happens to be has been altered, burned basically, but not melted, just metamorphosized through intense heat. The other kind of metamorphism, well, one of the other kinds of metamorphism is regional, and this is where pressure is the big key thing. Now, this is by far what produces the most metamorphic rock on our planet. Either we have pressure from tectonic plates colliding with each other, or the fact that if you go 50 kilometers below the surface, I don't know how much all of the solid lithosphere above you weighs, probably billions of tons perhaps, but that's an enormous amount of pressure, and it can cause the minerals, it can force the minerals to crystallize into new minerals, recrystallize, I guess we could say. And this has degrees of metamorphism as well. So the sedimentary rock shale, that can be metamorphosized through increasing heat, pressure, and time into many different metamorphic rocks, as a matter of fact. So here's a visualization of what regional metamorphism might look like. So we have the undeformed strata, the original sedimentary layers, and plate tectonics has caused them to warp significantly. So here's the shale, original sedimentary rock on the top left, and all these other four rocks are different kinds of metamorphic rock, just to different, they've been metamorphosized more intensely, basically, with increased temperature, pressure, and time. It can undergo several different evolutions, basically. What's important to keep in mind is we're not adding or subtracting any material. The original material is just being altered further and further and further. So, as I said, heat and pressure are sort of two sides of the same coin. We can separate them, but they pretty much always are in tandem. They work side by side. And as it metamorphosizes the rocks, the minerals change, and they change properties as well. A metamorphosized rock is typically much harder than the original rock that it formed from. The minerals, the gems perhaps that you find within it, are going to be highly tolerant to higher temperatures and pressures perhaps. And usually on the Mohs scale, they will graduate up higher as well and be very hard. Here are some garnets, just to show you some metamorphosized or mineral crystals formed out of metamorphism. So the final metamorphic process is hydrothermal solution, which we've covered several different times before, but basically this one is very different because it's actually the addition of new materials. Now, this could be considered perhaps like low-grade metamorphism. It doesn't really alter the existing minerals. It just deposits new minerals amongst them, adds it to the rock, forming ores in most cases. So here we can see, I don't know what kind of metal or metallic minerals have been added to this, but you would imagine there's some crack in the rock and superheated water carrying the metals works its way into there, cools, hardens, and cements them in place. It's now been metamorphosized. As far as classification for metamorphic rocks, it's very simple. We have foliated and non-foliated metamorphic rocks. So, sorry, I went too far. Foliated metamorphic rocks have distinct bands, usually of different color and different lightness or darkness. Now, when you squeeze rocks, when the existing minerals are put under enormous amounts of pressure, it can force the minerals to then line up perpendicular to the pressure. So originally, you want to imagine the mineral crystals are all orientated in completely random directions, but as they get squeezed with the intense pressure of metamorphism, they start to then, instead of being sort of in random orientations, they start to line up. And that's what causes this banding in most cases of foliated metamorphic rock. The non-foliated metamorphic rock, really nothing to say. They just don't have a banded appearance. Usually they're more uniform in consistency. There's only one type of mineral, so you can't really get bands because the bands often represent different minerals that are sort of contrasted against each other. So here's a piece of slate, which is metamorphosized mudstone or shale, for example. And that is going to do it for rocks, at least for now. So thank you for watching.